All right, so let's see this next one. It's the third one of this set of exercises. And here we are going to use the result that we proved in the previous exercise. In this one, we are going to recall a notion that we came across in this exercise 367, namely a set A having lesser or equal cardinality than another set B, and we say so when there exists an injective function f from A to B. When such a function exists, then we say that A has lesser or equal cardinality than B. Now, using the previous exercise, we have to show that if A has lesser or equal cardinality to B, and also B has lesser or equal cardinality to A, then naturally we expect them to have the same cardinality, and actually that is the case. So we have to prove this. Now, although we discussed about this notion, I mean when we discussed this exercise, when we solved it back then, but still let's just see why the condition is this. I mean there should be some reason, no? And this entire thing is actually a theorem known as Schroeder-Bernstein theorem, named after these mathematicians Ernst Schroeder and Felix Bernstein. So let's now see why this condition, I mean in what sense are we saying that A has lesser or equal cardinality to B? That is because of this. Because A and B are arbitrary sets, so they can be infinite, and hence the number of elements in them may lose sense. Okay, it may be meaningless. So that's why we are defining things in terms of functions. So the thing is like this. This is your set A, this is your set B. Existence of such an injective function means that you are having some things like this, some associations between elements of A and elements of B, so that distinct elements in A find distinct inverses in B. In fact, that's what injectivity means. So we can see that in a sense, B has at least as many elements as A has, but additionally there may be more in B or may not be. So in that sense, the size of A is less than or equal to the size of B, or more precisely that A has lesser or equal cardinality to B. Okay, so let's now see how this can be proved. Now, since we are going to have to use the previous exercise, so let us just recall the previous exercise before we start the solution. In the previous exercise, what we showed is this. Say we have three sets related to one another like this, A, B and C. C contains A and C contains B and B contains A as subsets, and there exists a bijective function from C into A. Then there exists a bijective function from B into A. That's what the previous exercise says. Okay. So now what is our hypothesis in this one? In this one, we are given that A has lesser or equal cardinality to B. That means there is a bijection from A to B. But also B has lesser or equal cardinality to A. So there is that was injection, okay, not a bijection. There is an injective function from A to B due to A having lesser or equal cardinality to B. But because B also has lesser or equal cardinality to A, so there is another injective function from B to A. So we have such functions. So that's where things start. Solution by the hypothesis there exist injective functions f from A into B and G from B into A. Okay, so this is F and this is G, and they both are injective functions. Then the composition G composition F, which is a function from A into A, is also injective. We know that the composition of two injective functions is injective. Hence, now this is injective, that we know. However, we don't know if it is surjective as well, and hence bijective, because the image set of this function, I mean the image of A under this function, may be a proper subset of A. In that case, it will not be surjection. But if we change this range and replace it with the image of A under this, then that function will be bijective, because it will be surjective besides being injective. So hence, from A into, now we replace A with the image of A under this is bijective. Okay. Now we come back to what we have here. This we understand, so we can just erase this. And now we come back to the situation at hand. Now, note that since F maps A into B, so F of A is a subset of B, obviously. F of A is the image set of the function and B is the range. That means what? It means that G of F of A is a subset of G of B, because we already know from the theory of functions that direct images of sets in the domain of a function behave well with containment. That is, if you have a relation like this, then the images of the sets under some function also are related in that way. So that means what? It means that G composition F of A is contained in G of B. But at the same time, since G is a function from B into A, so G of B is itself a subset of A. Now you recall the previous exercise and think of these sets in place of A. Perhaps I should not write like this, but you just think of these containment relations in place of this. Okay, that is, you imagine this in place of A, the intermediate set as G of B, and this set A as C. And what was our hypothesis in the previous exercise? That there is a bijection from C into A. Do we have a bijection from this into this now? Yes, this is a bijection, see? So that means what? It means that by the result of the previous exercise, there should be a bijection from B into A. That is that we should have a bijection from G of B into this. But we need to of course write these things. Note that since we have seen how this comes, we are going to write it directly. G composition F of A is a subset of G of B, which is a subset of A. So, by exercise 832, there exists a bijection, let's call it H, because there also we called it H from the intermediate set into this. H from, let me write it here, G of B into G composition F of A. Okay. Now we can think of another composition of not two functions but three functions that will give us what we want, and that composition is this. Since G from B, originally G was a function of what kind? From B into A, and it was injective. But now if we replace the range A with the image set G of B, then it will be bijective, because then it will be surjective as well. This is bijective the following composition is bijective as well, and that composition is this. G composition F inverse, composition H, composition G, and it's a map from B into A. But let's see what conclusion we have written here. We are saying that this composition is bijective. The first thing we have to see is that this is actually a map from B into A. What is the domain of G? B. Then G takes us from B into G of B. Okay. But then H is a map from G of B into G composition F of A. So from G of B we then go to this set, and then the inverse of G composition F takes us, inverse of this takes us from this into this. And note that all the three maps we have mentioned here, we have written here, are bijective. G is bijective. G means not the original G but this G. Okay, that is bijective. H is bijection, which we are getting from the previous exercise. And the inverse of G composition F first of all exists because G composition F is bijective. And again, we know that when the inverse exists, the inverse itself is also bijective. So that's why we are looking at a composition of some three bijections. So that itself is a bijection. So we have now found a bijection between B and A. That's it. So B and A, or A and B, same thing, have equal cardinality. So we see that the previous exercise, which was rather technical in nature, has this very nice consequence, that if you find an injective function from a set into another and also from that set back into this set, then they are bijective. Okay, you don't need to do anything with surjection at all. If you find two such functions, one going from here to there and another one coming right from there to here, and both are injective, that's it. The sets will be bijective. Have equal well, what did I say? The sets will be bijective. No, the sets will have equal cardinality. That's it. So that proves Schroeder-Bernstein theorem. Next, let us say that a set A has strictly lesser cardinality than a set B if A has lesser or equal, you can pretty much guess what we are going to write. When we define A less than B, where A and B are ordinary real numbers, how do we do it actually? We say that this is so when A is less than or equal to B and A is not equal to B. So that's what we are going to do here. So we are saying that A has strictly lesser cardinality than B if A has lesser or equal cardinality than B and A does not have the same cardinality as B. Maybe not, that's not how it's exactly given in the exercise in the text, but that's the meaning. Have the same cardinality as B. And A has lesser or equal cardinality than B, that is in the sense of exercise 367, but that's understood. We have already seen that in the previous exercise. Show that, okay, so now what is it that we have to show? Show that X has strictly lesser cardinality. Okay, now show that for any set X, X has strictly lesser cardinality than the power set of X. Okay, that is one thing. And also this other thing, also show that if A has strictly lesser cardinality than B, and B has strictly lesser cardinality than C, then A has strictly lesser cardinality than C. Now I need some ink though. The solution is actually quite easy because the hard part we have already completed in one of the theorems. Oh, okay, so you understand what this thing means. A having strictly lesser cardinality than B means that there is an injective function from A into B, but there is no bijective function between A and B. That's what this thing means. So the two things we have to prove are these: any set has strictly lesser cardinality than its power set, and also this transitivity between the strict relation. Transitivity of the strict relation. Solution. Okay. By, so we are going to first of all recall that theorem where we proved that X does not have the same cardinality as its power set. Okay, so that part we already have, and that theorem is theorem 831. X and don't have the same cardinality. So to prove our thing, it's enough to show that there is an injective function from X into this, because then the strictness of cardinalities will be established. So it's enough to find an injective function from X into its power set, and one such function is this. Where f of x is defined to be the singleton set consisting of x. Now I am going to leave it like this. Okay, it's absolutely straightforward to verify this, but still let me just do it orally. Is this function well defined? For any element x in X, we are getting a unique subset of X. A singleton set, but that's a unique subset of X. So yes, this function is well defined and this output belongs to the range. And then is it one-to-one? Say you take two distinct elements x and y in X, then their f images are the two singleton sets, one consisting of X and the other consisting of Y. Because the elements themselves are distinct, so the singleton sets are also distinct subsets. So yes, the function is 1 to 1. Okay, so that's just it. That is one half of the claim. Now the next half. In the next half, it's given that A has strictly lesser cardinality than B and B has strictly lesser cardinality than C. So we do that in another paragraph by the given hypothesis there exists injective functions. What should we take? Let us call this G and H, or say A and B. A and B, A from A into B and B from B into C, which just say that A has lesser or equal cardinality than B and B has lesser or equal cardinality than C. But now we come to the strictness part also. And no bijective functions say alpha, no such functions. Okay, so we are saying that something does not exist. If you want, you can write A here and B here also, because bijection, non-existence of a bijection from A into B is equivalent to the non-existence of a bijection from B into A. And beta from C into B. Now, obviously, we can compose these two to form a bijection from A into C. Decomposition A from A into C. Well, I mean injection. Why do I keep messing up these things? This is an injective function, this is another injective function, so their composition is an injective function. This is an injective function. But our that's simply not enough. This tells us that A has lesser or equal cardinality to C, but we need to also prove that they cannot have the same cardinality. Suppose we forcefully suppose that they are of the same cardinality. Suppose there exists a bijection, say from what should we call it, say gamma, from C into A. Then gamma being bijective is also injective. Gamma is injective, and hence now we can take the composition of gamma and one of these two. Which one should I take? If I take the gamma and A, and hence, but how will it go? First we go from C, so it will be A composition gamma. from C into B is injective. First, gamma takes us from C to A, and then small a takes us from A to B, so C into B. This is already an injective function, and this is injective because it is bijective. So now note that we have found an injective function from C to B, but already we have another injective function from B to C. So we are able to use Schroeder-Bernstein theorem. But then by Schroeder-Bernstein theorem. I am not sure whether I should use a "the" here, but anyway, by this result, there exists a bijection, say, let me call it delta, between B and C. Or because we are going to write about something that is wrong, so let's write from C to B. But then that is just simply in contradiction to this. Here we are saying that no bijective function is possible between C and B, but then we have this, and this contradiction stems from our supposition here. So our supposition is wrong. What was our supposition? That there exists a bijection between C and A, which hence does not exist, and already we have a bijection from A into C, and as a result A has strictly lesser cardinality than C. That's what we wanted to show. So you can see that in these last few exercises, we are really not doing anything. Doing anything means we are really not using any construction or doing something new, but we are cleverly using whatever we already know. Then C. So that is the solution, and there is one more, so let's just finish it. This one is very nice. This last one, show that no power set i.e. a set of the form this for some x, that means for some set x, no power set can be countably infinite. Countably infinite means having a bijection with the set of natural numbers. That cannot be. Okay. No, you cannot find a power. cannot find a set X for which its power set is in a bijection with n. And the proof is, of course, by contradiction, and the proof goes like this. Suppose the opposite. Suppose there exists a set X for which its power set is countably infinite. Okay, then there is going to be a bijection between this power set and n. Then there is a bijection. I have given it a name G. G because I have reserved F for something else, since there is an injective function f from x into its power set. It's that injective function which maps every element onto the singleton set given by that element, and we came across that in the previous solution. Okay, so we can now compose these two functions and get an injective function. This is injective, we already know, and this is also injective because it's bijective. The composition G composition f, which is a function from x into n, is injective. But when there is an injective function from x into n, then x becomes countably infinite. This is a result that we already have seen. Well, I should not have said countably infinite, but at most countably. It's either countably infinite or finite. But then, and the term for that is at most countable. X is at most countable, and the place where we saw this is exercise 816. You go back to that exercise, you will see. Now, being at most countable, x is either countably infinite or finite. Now, if x is countably infinite, then there exists a bijection, say it theta, say, from x into n. Okay, but we already have another bijection from this into n. And we can use these two things, that is, we can compose these two, not exactly these two but something else, to create a contradiction. But then G inverse composition theta is a function from x into its power set, because theta takes us from this to this, and then G inverse takes us from n to this, is a bijection which contradicts theorem 831, because here we have proved that there can be no bijection between a set and its power set, so that is the contradiction. So x cannot be countably infinite, but x is at most countable, so that means x has to be finite. And consequently its power set also has to be finite. But then that itself creates a problem. And consequently this is also finite, and in fact it's our first exercise. But this contradicts our supposition. What was our supposition? Namely, that there is a bijection between the power set of x and n. Now, if the power set is finite, how can there be such a bijection? Because we already know, in fact we proved that the set of all natural numbers is infinite. Hence, our supposition is wrong. That is, this cannot be countably infinite for any set x. If x is finite, then it is also finite. But if x is infinite, then we know that it's infinite, but it cannot be countably infinite. It will be an infinity larger than that. Okay, so that's the consequence of all these things. So that's where this solution ends, and our current exercise set also ends. So that means next week we will start the next section on axiom of choice, the last axiom in our ZFC, that is Zermelo-Fraenkel choice set of axioms. And our next upload is this coming Tuesday. And on Tuesday, what should we do? We have already gone through what are the things that we went through recently. Group theory from Herstein we have seen, right? Calculus also we have seen, vector spaces we have seen recently. So what else is there? Oh, field theory, yeah. So on Tuesday, let us going to see extension fields, and that's just it. That's it for tonight. So see you on Tuesday. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.